I think a really important idea with derivatives is higher order derivatives, and I believe this is taught in high school, right?
Yeah. Yeah.
For sure, yeah. So higher order derivatives, and I think the best example for this is think of the exact same thing that Parker was saying with a ball that you drop from 1 meter high. Right? Now, if you want to find the average velocity, as he said, you simply take your distance and you divide it by your time. But now, remember, when you drop your ball, right, zero speed, somehow it has X amount of speed when it hits the ground. So it obviously accelerated. So now, if you want to calculate the acceleration of this ball, then what do you do? So the acceleration is basically a rate of change of the rate of change. Let me explain.
So remember the golden word, right? The golden word of calculus is rate of change. Exactly. So if you take a derivative, you find the rate of change at a point. If you take a second derivative, you're finding the rate of change of the rate of change, which, if your speed is increasing, then you're accelerating. If your speed is decreasing, then you're decelerating. But if you're going backwards, and then you're going backwards faster and faster, then you're technically decelerating because you're going more and more negative.
More backwards. Exactly. Yeah, so I mean, that's where the second derivative, the third, like all these higher order derivatives come into play, right? Where higher order, like for example, as we were just saying, like acceleration, kind of the rate of change of the rate of change, right? Where velocity itself is meters per second, acceleration is meters per square second. So what you're basically doing is you're simply taking the rate of change. Yeah,
meters per second squared.
Second squared, so square seconds. That's what it's square seconds.
Okay,
sure. You know how you say square centimeters? It's the same thing. Square seconds. Kind of thing. Okay. Anyways, so even higher order derivatives, like I think it's the fourth, fifth, and sixth derivatives of position with respect to time, is known as snap, crackle, and pop. You guys might have heard of that. I don't know. I just really wanted to mention that. Have you never heard of snap, crackle, pop? Okay, so if anyone's a Rick and Morty fan out there, definitely send us an email because I would love to meet some Rick and Morty fans. But yeah, so snap, crackle, pop is just like, they say it sometimes, and it's basically the fourth, fifth, and sixth derivatives of position with respect to time. So it's basically like if you differentiate acceleration, you get something called jerk. So like how fast your acceleration is changing is called jerk. Right, and it kind of makes sense because it's kind of like let's say you're jerking in a vehicle, right? You're basically jerking back and forth.
That did not come out right, man.
I mean, okay, that sounded so wrong. That's not what I meant, and you know it. I meant back and forth, man. You understand that? Obviously, for the non-viewer participants, you might have not seen that thing that I was doing, so it might have not made sense.
You said we're jerking in a car back and forth, man.
Okay, I apologize for those choice of words, but I think people understand what I'm trying to say. The change in acceleration over time is the jerk. I mean, that's just what it's called. And then when you differentiate the jerk, you get snap, crackle, pop. Wait, right? Because acceleration is 2, 3. Yeah, then you get snap, crackle, pop, I believe. So I mean, not that it's anything important. It's just. But
do you know what those things are?
I mean, as I said, it's just the fourth, fifth, and sixth derivatives with respect.
Yeah, but what do they represent?
That's all they. I mean, they're just cool words, I believe. Okay. I don't think they represent anything. I mean, okay, I could be wrong. It's just that I heard of this because of Rick and Morty, and I searched it up, and I'm like, oh, that's cool. So
yeah, I mean, obviously, it's going to be the rate of change of the rate of change of the rate of change. But what does that mean physically if you're talking about velocity and?
Yeah, again, I think it's a little hard to explain that way because I think up to jerk is really where all you can really kind of visually explain and understand. But I think beyond that, rate of jerk, this sounds so wrong, bro. It's so weird. But you know what I mean? Like the rate of jerk with respect to time, what even is that?
Okay, let's just move on here.
Let's just move on. So those were higher order derivatives.